Welcome back everyone. We're going to be working on undirected graphs today. So let's consider an example here. We're a hockey team competition with 6 teams, A, B, C, D, E and F, and the following is known. And I won't read it out, but you can see that A's played a few and beaten them, B, also C, D, E and F. So when we graph this, this is the graph that we get. Now the E, the D, the A, B, C and F, these things here that I'm shading in right now, they're called teams, tasks, towns. That's what they could be. Could be anything at all, but we know them as vertices, or another name for them being nodes. Vertices A and B, because they are known as adjacent vertices because we have an edge that goes from A to B. Okay. Now this graph we can represent it by a table or a matrix, where we have 1 being used if there's an edge connecting the 2 vertices, and a 0 being used if there's no edge connecting the 2. So for the above, this is what we get. I'm not going to go back, but there was no edge connecting A and A, so 0 there. 1 for the B, A to B, nothing connecting A to C, so 0, nothing connecting A to D, and then A to E there was 1 edge, and A to F there was an edge. Then B to A, 1, B to B is 0, B to C is 1, then we had 0, 0, and B to F is 1. Now I'll quickly fill them in, 0, and we'll go down the column, so 0, 0, 1 and 1, and then the next one is 1, 0, 0, 1, and the next one is 0, 1, 1, 0, and the next one is 1, 0, 0, 1, and E is 1, 0, 0, and F is 0, 1, 0, 0. Okay, so that's the actual table. Now this is, we can also do that as a matrix. It's exactly the same, except of course instead of being in a table, we have it in a matrix form. So again, we're just going to quickly fill them in, okay, and we'll again I'll fill these 2 in and we'll go down again. So 0 there, 1, 1, and underneath the C, 1, 0, 1 going across, and then straight down is 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, and 0, 1, 0, 0. And this is known as the adjacency matrix. Now if there's more than 1 edge linking 2 vertices, then we call it a multiple edge. Okay, so let's have a look at one. There's one there. We've got a multiple edge at A and C. You can see that there are 2 edges that connect A and C. We also have a loop at B. Now excuse the loop, I sort of couldn't get the right angle of it, but it's supposed to be a circular. Okay, and E is sitting all the way by itself there with nothing that connects to it. Okay, and you'll realise that later on that this is called an isolated vertex.
I'll just write that one down. This is called isolated.
Okay, so isolated vertex. Now let's do an example. It says construct a table and matrix corresponding to the graph shown, which represents 3 houses, A, B and C, connected to 3 utilities, gas, water and electricity. So there we have the graph.
But this is also called a bipartite graph, isn't it?
It is called a bipartite graph. The reason being is because we have partitioned this into 2 disjoint sets, A, B and C being the houses, and G, W and E being the utilities. So you can see that we can sort of draw a line between them and they are split. So, alright everyone, so we're going to be doing a matrix here by itself. We won't do a table because the table, as you can tell, is the same. So straight across the top we've got our houses A, B and C, and we also have our utilities G, W, E, and of course we need to do that along the side as well, because we have to be able to show whether they connect to each other or not. So we know that house A does not connect to house A, so we put a 0. And house A, of course, does not connect to house B or to house C. So it's 0, 0, 0 straight across. And then it does connect to the gas, water and electricity. So you put a 1 there, a 1 and a 1. House B, of course, does not connect to any of the houses, so it's 0, 0, 0, and then 1, 1, 1 again. And house C is exactly the same, can't connect to the houses, but will connect to the gas, water and electricity. Then when we're looking at it from the utility side, it changes. So the utilities do connect to the houses, so we've got 1, 1 and 1, but the utilities don't connect to each other, so we've got 0, 0, 0. And that belongs to all the utilities as well. Okay, so we have to make sure that we do that properly. And we have to show them all along the top and along the side because we have to include every vertex. Now the degree of a vertex, that's the number of edges that come from that vertex itself. Okay, that's the degree. So, and we should be putting brackets around degree of A, so DEG, brackets. The A should be in there, and they should all be there, so even the B and the C and the D and the E. Okay, so we need to put brackets around all of them. Now the degree of A, how many vertices, how many edges are coming out of A? Well, there's, if you count them, there's 1, 2, 3, 4. So the degree of A is 4. How many edges are coming out of that one? Out of B, there is 1 and 2. Don't include the loop twice. There's only 2. Out of C, if we count them, there's 1, 2 and 3. That's not a loop, they're 2 different edges connecting A and C. So we've got to count them both. Degree of D is 2, and good old E sitting out there all on its lonesome, which of course is 0. There's nothing that connects it. Alright, the graph below is known as a simple graph. There are no loops and there's no multiple edges. Now for this graph, the sum of the degrees is equal to twice the number of edges and is even. Okay, the sum of the degrees is equal to twice the number of edges and is even. So there's the sum. We've got all the degrees, 3, 2, 2, 3 and 2. Adding them up, we get 12. Okay, 12. So it is even. We've worked that out. And it's twice the number of edges. Let's count the edges. 1, 2, 3, 4, 5, 6. Twice 2 times 6 is 12. Okay, so for a simple graph, that actually works out. Okay, so be aware of that. Sometimes it's easier to quickly work that out if required. Alright, a path. A path is a series of vertices connected by edges. A graph is said to be connected if there is a path between each pair of vertices. Okay, so there's got to be a path between each pair of vertices. So let's have a look at an example. There we go. A circuit is a path which starts and finishes at the same vertex. So if it starts at A, it's got to finish at A. If it starts at B, it's got to finish at B. And you can't travel along the edges more than once. Okay, so you can only travel along the edge once. So for the above example, here's an example of a circuit, and I'm starting at A, B, to C, to D, to E, to F, and back to A. I've only travelled along each vertex once. Or I could go E, F, D, and back to E. Okay, but we should incorporate all the vertices. A subgraph, that's only part of the graph, so we don't need to have all the original graph listed. Okay, so it's only part of it. That's it. 23A is the what you're doing now. Thank you.